Welcome to an introduction to virtual wide area networks. For nearly 15 years, network architects have been virtualizing their local area networks to partition traffic. Now these architects are migrating physical servers to virtual machines. They are also applying similar strategies to data storage. With over 1 billion PCs currently in use throughout the world, desktop virtualization holds the potential for significant long-term savings, even if the payback is a little more protracted. Virtualized architecture is now being clustered and distributed beyond enterprise boundaries. Hybrid cloud architectures are being built from combined private enterprise and public managed platforms. Desktop computers, whether virtualized or not, are rapidly being replaced or supplemented by laptops, smartphones, and tablet devices. These mobile devices are spending more and more of their time outside of the traditional enterprise boundaries. So, with LAN virtualized, servers and storage virtualized, the managed cloud platform virtualized, and with desktop virtualization being addressed within the enterprise, where is the virtualization of the wide area networks that is needed to connect them together? At Brand Communications, we believe that this missing piece of the architecture needs to be created if the full promise of virtualization is to be realized. This is the role we see for virtual wide area networks. Virtual wide area networks are like virtual local area networks. Virtual local area networks logically separate a single network so that it can be used as if it were multiple networks. Virtual wide area networks logically combine multiple networks so they can be used as if they were one network. They can be comprised of as many similar or dissimilar wide area networks as are available or needed, but for clarity we will show only 3 in this introduction. There are 2 nodes in a virtual wide area network. They are connected together using Layer 2 tunneling protocol. This means that both nodes are effectively on the same link layer and behave as if they were a distributed switch. Layer 2 tunneling protocol is an IETF standard that defines one node in the role of a client and another node in the role of a server. In practical terms, once the nodes are connected, they become peers. Multiple client nodes can simultaneously connect to a single server node at the same time. Virtual wide area networks can be established between client and server nodes over multiple networks at the same time. This is called bonding. As each new network is connected, the client and server nodes add its bandwidth to the pool of already established networks. The aggregated bandwidth of all available networks is then presented to attached devices. Should a network become unavailable, its bandwidth is immediately removed from the pool and the virtual wide area network continues. The client and server nodes can also decide on a network preference that places all but the preferred network in a hot standby mode. This is called roaming. In the event that the preferred wide area network fails, the client and server can immediately switch the traffic to a secondary wide area network. Should the secondary network become unavailable, the client and server nodes seamlessly switch traffic onto a tertiary network and so on. If a more preferred network becomes available, the client and server seamlessly switch traffic to use it. From this point forward in the presentation, we are going to focus on the specific features of Apollo, a software-based virtual wide area networking platform from Brand Communications. When an Apollo client node first connects to an Apollo server node over a wide area network, they perform a comprehensive authentication. First, the client node assists its network interfaces to authenticate with their respective wide area networks. Next, the Apollo client and server nodes authenticate each other to establish a secure L2TP tunnel. To complete the authentication, the Apollo server node interacts with any upstream AAA server to authenticate the client node user, whether that user be a software application or a human being. Once authenticated, the Apollo client and server nodes commence configuration. The Apollo client node stores a policy that is used to configure its behavior prior to connecting to the server node. This might include such preferences as what wide area networks to use, what virtual local area network to join, and which protocols to prioritize. The Apollo server node also stores a client policy which includes additional parameters such as the IP address that the client will assign to a connected device. The server policy is set to override the client policy, providing administrators with the ability to remotely control and configure all aspects of the client node. One of the most important functions undertaken by Apollo's client and server nodes is measurement of each wide area network's performance. Information such as bandwidth, throughput, delay, jitter and packet loss are gathered as each network connection is established and on an ongoing basis during its usage. The client and server perform these measurements simultaneously for each uplink and downlink, giving a complete picture of the wide area network's performance. As each additional network becomes available, the measurement process is repeated. In this example, all of the connections are wireless, but in practice, the wide area network might be all fixed, or there may be a combination of wired and wireless. Apollo's client and server nodes perform a comprehensive deep packet inspection that identifies the protocol type of all traffic being presented to the virtual wide area network. Apollo transparently supports VLAN traffic and inspects for the presence of VLAN tags. The Apollo client node can terminate VLAN traffic on the local machine on which it is running, or it can be passed to an attached switch via a VLAN trunk, or both can be configured at the same time. Once the traffic is inspected and identified, it can be shaped and presented to the virtual wide area network. Policies such as which wide area network to prefer, which protocols to prioritize, and how to manage VLAN traffic are applied. Traffic is then assigned to the virtual wide area network based on the measured performance of each of the available connections. Here are some examples of how Apollo shapes traffic. Apollo allows applications to address the bonded bandwidth of all wide area networks. This unique feature uses a wide area switch network architecture at layer 2 that addresses the bonded bandwidth of all available networks as a common pool. Quality of service is maintained for priority traffic by shaping other traffic around it. Applications do not need to reserve bandwidth in advance. Apollo has built-in jitter busters which ensure that delay-sensitive protocols such as Voice over IP are optimized across the virtual wide area network. Voice over IP traffic often has to share the virtual wide area network with other protocols. When this occurs, Apollo reduces the packet size of the other protocols to limit the serialization delays experienced by the voice packets. The result is significantly better quality of experience for voice applications, especially when bandwidth is limited. When multiple networks are available, Apollo ensures that voice over IP and other delay-sensitive traffic is sent by the lowest latency network. If the lowest latency network becomes congested, Apollo can also seamlessly switch delay-sensitive traffic in real time to use multiple networks, preserving the user's quality of experience. Apollo selectively compresses and decompresses traffic across the virtual wide area network. It also encrypts traffic using an AES 256 algorithm at layer 2 with low overhead key management. This low overhead is especially important for encrypting voice over IP traffic, the performance of which is adversely impacted by the overhead of other encryption protocols such as IPsec. Apollo maintains the integrity of the encryption between client and server nodes as multiple networks are bonded together. Encryption is also maintained when the virtual wide area network roams between different networks. When all wide area networks are disconnected at the same time, the Apollo client and server nodes simulate a congested network to connected devices. This state continues until one or more of the wide area network connections is re-established or the virtual wide area network is terminated. Apollo also ensures that the encryption persists until the session is restored or is terminated by the client or server nodes. Here are two use cases that illustrate the benefits of virtual wide area networks. The first is mobile. In this use case, Apollo server software is deployed at the edge of an enterprise LAN or on one of the many edges present in a carrier network. Apollo client software is loaded onto a PC, a smartphone, or one of many variants of mobile appliances. When the client and server are connected via a virtual wide area network, the mobile device receives an IP address from the client node that is assigned to it by the server node. From that moment onwards, the mobile device behaves in every respect as if it were on a subnet of the remote enterprise or carrier network. Bandwidth between the mobile device and the remote network can be enhanced by bonding two or more wide area networks together, such as two 3G networks, or a 4G network and a DSL connection. For example, this feature is important to users who need to stream surveillance video, or to service providers who want to increase the quality of experience for their unified communications applications. Connectivity is also maintained seamlessly as the mobile device changes bearers, such as when moving between 3G and 4G, or between 4G and Wi-Fi networks. This feature addresses problems currently being experienced by carriers seeking to offload traffic from congested 3G networks and by enterprises seeking to control the cost of their employees' mobility by using least cost networking. The second use case for virtual wide area networking is cloud-based virtualization. The Apollo server software is installed on the edge of an enterprise network. The Apollo client software is installed onto a virtual machine image within a managed cloud platform. When an instance of the image is launched, a virtual wide area network is established from the virtual machine, through the virtual NIC, across the wide area network back to the server. The VM is now using an IP address allocated to it by the server and behaves in every respect as if it were on a LAN subnet. This includes the ability to assign each virtual machine to be part of an enterprise VLAN. This feature is important to hybrid cloud administrators because it allows virtual machines on public cloud platforms to be configured and managed as an integral part of the enterprise network, even though the resource is remote. Connectivity between cloud virtual machines and enterprise networks is maintained seamlessly over multiple bonded wide area networks when increased bandwidth or reduced latency between the virtual machine and the enterprise LAN is demanded. Virtual machine connectivity can also fail over to backup networks for increased reliability and disaster recovery. Thank you for watching this introduction to virtual wide area networking. If you want more details on these use cases, please review our other videos.